Hey everybody, my name is Tam N. I'm a tutor here at Chegg, and today I'm going to be talking about digital circuits. So what a digital circuit is, it's a circuit, except the special thing about it is that it has only two states, alright? It represents two discrete levels, and that's a 0 or a 1. So what exactly does that mean, 0 and 1? Well, 0 is a low voltage, 1 is a high voltage, and we can just see this as a switch being on or a switch being off. Or you could even think about it as true or false, right? So is the switch on? True. If the switch is off, false. But we think of it as zeros and ones, because it works easier with our binary counting system. Binary is base 2. Normally we have, base 10, we have numbers with 10 digits. But in base 2, there's only 2 digits, right? So everything's in ones and zeros. So we have a signal here to the right, and we can see the signal is just a square wave, right? It's not analog, it's digital. There's nothing in between. There's only a 0 or a 1. It can't be anything else. So in this little square wave here, we have low voltage, alright? I should have mapped it. This could be time. The x-axis is time. And technically, the y-axis is not really voltage. It's more of just a discrete state, right? 0 or a 1. So as time goes on, we have a 0. And as it goes up, we have a 1. And it goes back down, 0, 1, 0, alright? So what we have here is 0, 1, 0, 1. Oh, that's not right. 1, 0. Now, why do we need this? Well, digital circuits are used to perform Boolean logic. And in Boolean logic, there's 3 universal gates or operators, right? In digital circuits, we call them gates. And those gates are the AND gate, OR gate, and the NOT gate. And in Boolean logic, or Boolean algebra, the AND is seen as a conjunction, OR is disjunction, and NOT is just the inverse. So when we're designing digital circuits, this is what the AND gate looks like, what the OR gate looks like, and what the NOT gate looks like, right? We can express it in an equation like so, where AND, you simply multiply them. It's the same thing as if you multiply them. So A, B, or some people even put A dot B. It doesn't matter, it's the same thing. OR is represented by a plus, right? So we have signal A plus signal B. That means A or B. And then NOT is simply just a little bar on top, right? So this is called A NOT. So let's see what they mean. Below I have a truth table. What a truth table is, it's simply just a little table where you list all the possible combinations for the signals you have and its outputs. So here we have 2 inputs, A and B, 2 signals, and goes from the possible combinations is A is 1, B is 1, A is 1, B is 0, and so on until there's nothing left. So the AND gate A and B will only be 1 when all the inputs are 1. So that's what I have here, 1, 1. 1, everything else is 0, right? Because there's no other time when A and B are both 1. The OR gate, in order for the OR gate to become a 1, the output to become a 1, there has to be at least one 1, if that makes sense. There has to be at least a single 1 in the inputs. So here, everything's a 1 except for when they're both 0, right? And then for the NOT gate, this one is the easiest one. You simply take your signal and you invert it. It becomes the opposite. So if A is 1, then A NOT, there should be A NOT. A NOT is 0, and when A is 0, A NOT should be 1. Okay? And these are how you draw them. And you can do some really useful things with these gates. we call these the universal gates because you can create all the other gates. There's several other gates, like you have the XOR, the NOR, XNOR, but we're not going to go too in-depth in this video about those gates. So these universal gates, they make up all digital circuits essentially. Every single device that uses logic can be created with these three gates. Let's take a look at one of these such devices. Okay. Let's say I want to make a special circuit that unlocks a lock when I input a special code, right? Maybe the code is activated by levers or buttons or switches or something, okay? So how am I going to do that? Let's say I want to make a special code where I have 6 little switches, right? I'm going to make them little buttons. And I want it so the lock will only unlock when this one is on, this one's on, and both of these are on. Okay? And that's the secret code. So we can represent this as 1s and 0. Alright, we'll say on is 1, off is 0. Oh. So we can think of this as our special code. We have 1 0 1 0 1 1. So this button is on, this button is off, on, on. Okay? And with this secret code and only this secret code, then our lock will unlock. So let's go ahead and see how we'll do that, alright? So I'm going to call these, by the way, switch A, B, C, D, E, and F. Alright, so I have, I'm going to have an AND gate here. Okay? And this is A and this is signal B, alright? So when is this AND gate going to be on? Well, notice we have an inverter here. Normally it would only be on when A is on and B is on. Or A is 1 and B is 1. But since B is inverted, now A, or this output here, will only output if A is 1 and then B is 0. Because if B is 0, the output of this inverted signal is 1, right? Okay, now we move on to C and D. Okay, C is 1, D needs to be 0 for a secret code to work. So we're going to put an inverter there, or a NOT gate. We have C and D. And then E and F needs to be 1, so it's just going to be not inverted. Okay. Now look what we're going to do. We're going to take these two output signals, we're going to attach them to another AND gate. Okay? And with that output, we're going to AND it with this final AND gate. And we'll call this F. Okay? So let's analyze the circuit here and see what it's doing. So we have a total of 5 AND gates and 2 inverters. Alright, so this one we can call A not B, C not D, E F, right? Because it's ANDed together, so imagine a little dot in between them, it's like we're multiplying. That's a good way to think about it. Okay, so when A is 1 and B is 0, only then will this output be outputted. And if C is 1 and D is 0, only then will this output be outputted. See where I'm going here? A has to be 1, B has to be 0, C 1, D 0. It follows our secret code. Alright, so once we AND that signal together, we can AND this one. And this one will finally be A, B naught, C, D naught, E, F. Oh, looks like we already have an F, so maybe we shouldn't call this F. Let's call it Z. Okay? So Z will only be outputted, alright? Z will only have a 1 if we have the secret code. If A is 1, B is 0, C is 1, 0, 1, 1. Alright? Let's attach Z to some sort of locking mechanism. Okay? So once we input our special code, only then will Z will unlock. If any of these are off, Z will never ever be 1. Okay? It has to be this specific code. We can simplify this circuit down. We can make it a big ol' AND gate. And AND gates don't have to have only 2 inputs. They can have as many as you want them to. So we'll have A, B, and to invert the signal, a lot of times you'll see this little circle right before it goes in the gate. That means invert. Okay, so we're going to take that signal and invert it. C, D, E, F. So it looks kind of like this jellyfish thing, right? Okay, so what all this does is that outputs a single output Z, or whatever you want to call it, only if we have a special code. And this device actually has a name, and we call it a decoder. And that's just one of the things you can do with these logic gates. So you can make a decoder. These 3 logic gates here that I have shown you create the basis of all digital circuits. They take discrete signals as input, and they output one discrete signal after doing some sort of operation on them. The reason they're so important is because they're the building blocks of all complex digital circuits. If you tear them apart and look how they're made, they will be made of these 3 gates. This concludes our lesson on digital circuits. My name is Tam N, and thank you guys for watching.